Hello everyone. This is again another video on the OnStep Telescope Controller project by Howard Dutton. And in this video I'm going to cover the spreadsheet that is used to calculate the values for your specifics of the mount, mechanical and electronic properties, and the motors, and how to use the online configuration generator to generate a configuration that would work out of the box without having to edit files or anything like that. So first of all, you need to get the spreadsheet that is the OnStep configuration calculator. This one is, so if you go to the wiki, you'll find the link to it. It's on Stellar Journey, the website of Howard Dutton. So what this spreadsheet provides is that you enter values for axis 1 and axis 2. Axis 1 is the right ascension or the azimuth for the right ascension for equatorial mounts, and azimuth for alt-azimuth mounts like Dobsonians. And the other axis, axis 2, is the declination or the altitude. So you should know several things before you start. How much steps per rotation for your motor. So the motors there are different types of motors. The best ones seem to be the 400 steps per rotation, which is the 0.9 degrees per step. And then you would need to know the characteristics of the stepper drivers that you have. So there are various stepper driver models. The TMC2130 seems to be the best one with the SPI configuration, but there are others like the LV8729 and of course the cheaper DRV8825 and the A4998. I can't remember the exact number. And then you would need to know the reduction of the gearbox. So from the motor to the worm gear, what is the reduction? So some stepper motors have the reduction inside the stepper motor itself. It has a gear planetary head or something, and it would provide a high gear ratio. If not, then there would be either two gears or two pulleys that would do this. So if you get a pulley, for example, and you have the most popular size 16 and I think 40, that would give you the 3.75. And then there is the how many teeth on the worm wheel, which is basically the thing that is driving the axis of the computer, of the telescope itself, the mount. And you do the same for the other axis, and you would come up with values like these. Now these values, you're supposed to edit the file and put them in, but I'll show you an easier way. But then before you leave this spreadsheet, here is how many rotations per second the motor would have, rotations per minute, and the same for the other axis. And this would give you the resolution of the tracking. So when the mount is doing sidereal tracking, how many arcs per second it's doing. So anything under, say, 1 arc per second is more than acceptable, or 0.7 arc per second. There are some hard limits here that you should not exceed, and the same goes for this value, the max rate. And it gives you here, depending on what you're using. So the Mega 2560, the Arduino Mega, is the least powerful of these, so you have to use a high value. And the TNC is there are several versions of it, and you can use different values here. Now when you change these values, you will see that the maximum slew rate, which is basically when you're doing go-tos. So if you use, for example, 32, your maximum slew rate drops to 3.26. Let me zoom in a bit on the on the spreadsheet so that we can see things better here. Okay. Okay, so I hope this is more visible. So if you're using a cheaper motor with 200, then you can enter that value here. Or if your mount may already have motors in it, and you may just want to change the controller to get more functionality. So your mount may already have a stepper motor, but you need to know the characteristics of it, and you need to know how to drive that. So if you have already a 200 motor, or even a 48 motor, the older ones. I have a friend who has a mount with already 48 steps per rotation, and we're working on his mount to get things started with converting it to OnStep. Okay, so once you do that, then you come up with these values. You're confident that these are do not exceed the mount's limits. Let us, for example, change here to 16. Okay, and because I'm using STM32, which is as fast as the TNC3.2, 72 megahertz, then I can get up to a maximum slewing rate of 13. Now, whether this is realistic or too fast, we will know, I mean, how things are. Now, note that when I use the motor with 200 here, the tracking resolution dropped to 0.7, which is perfectly fine for visual observation. For astrophotography, I don't know if that is acceptable or not. But if you're using any of the TMC stepper drivers, it does interpolation of the steps to 1 over 256. So it really doesn't matter much. Or you can set the stepper to 32. So you have to have a stepper driver that does 32, and you see that this drops back to here. And the slew rate goes again to 6.51. Anyways, there is a lot of discussion. You can ask, there is the OnStep group at groups.io. There is an OnStep group there, and you can ask questions. Howard is very helpful and would answer your questions, and there are others who know the mechanical and electronic parts much more than I do. I'm just a beginner when it comes to those, but I just work with the firmware part of OnStep. So let's say I'll settle for 6.5 degrees per second for go-tos, and 200 step motors, the cheaper ones, and 32, and let's see how these goes. Okay, so what you need to do is to go to the online configuration generator, which is here's the URL. So the URL is o.bahieldin.com. So Bahieldin is my last name, and I have a domain based on that. But then you have to enter 1111. So the links is, I'll put the link in the description of this video. You don't have to read this fine print here. Okay, so this is the online configuration generator. Basically, it just tells you where to download the spread, the OnStep itself. So the recommendation is to use the beta. Okay, let's focus a bit on these parts. So if you go here, then if you click here, you'll get the beta version. If you click here, you'll get the alpha version. Which one to use depends on your needs, whether you need certain new features and risk a little bit of instability, or go with the stable version that has been tried and tested. This is a link to the spreadsheet, and you would download that before you go into the configurator, into the configuration generator. And then there are the configurator generator itself. Okay, so let's see how the configuration is done. So first thing, you have to select whether your mount is equatorial or altitude azimuth mount. Altitude azimuth is mainly for Dobsonians. Equatorial is for many other mounts, and there are also the old fork mounts. Some people still have those, and they have certain features like they don't need a counter weight, and they can go from horizon to horizon without an azimuth, without a meridian flip. Second, you have to select your platform, whether you're using ramps, which is for a Mega, Arduino Mega, or using the mini PCB or the max PCB that were designed by Howard. The mini PCB uses the TNC3.2, which is I think around $20 or so. The max PCB is around $35. The TNC 3.5 and 3.6 are around $35 or so. I can't remember if these are US or Canadian. I haven't looked in a while. And then there is the STM F1, which is, you can get it for $3 for the small board, or for the other board you can get it for $12, $13 for the bigger one. In speed, they are equivalent to the mini PCB, but you still need to do the wiring and all that. Hopefully over time there would be boards based on that and would be less cost. Okay, so let's select the STM32, and then the max rate, I'll go to the spreadsheet, and okay, so it's 16. Okay, let's put 16 in here. Okay, and then for the PEC buffer size, again I need to go to the spreadsheet. 600 is the value for the 144 teeth, so we'll do 600. Okay, and then upon startup, do you want the OnStep to do the sidereal tracking or not? Initially, when you're testing, I recommend that you turn this to yes, simply because you don't have to go and connect the controller to a PC and start sending it commands for alignment and tracking and stuff like that. So it will give you a visual feedback if you have an LED that is enabled on the board or in your circuit. So it avoids a step. Whether you want to turn this off later or not, it's up to you. Howard does not recommend that this be set to yes, but if you, for initial testing, I recommend that you turn it on. Okay, so the next thing is the steps for the motors, and you can see that they are 200 steps already. There are various motor options. So for 100 steps, there is 100 steps, and there is the 48, the old small motors, and some mounts still have these. You can select this depending on what your mount has. And then let's see what is the Microsteps, and you can see here in the description that I use the same order as the spreadsheet, and the names of the columns are bold in bold. So here I chose 32, so let's select 32 here. Okay, and 32 for the other axis. And here I'll just leave it at 1, which is the difference between the go-to and go-to is the bottom one, and sidereal tracking is the other one. The transfer gears, so here it says 3.75, so I'll just put 3.75 here. Okay, and the same for the other axis. Now, sometimes you would end up with different motors and different axis and different gearing for different axis, but usually it's the same. And then the worm wheel, how many gears, how many teeth per, how many steps per the full rotation. So it's 144 for both axes. This is the most common value for the EQ5 type mounts. And then here is where you select the driver that you're using. So depending on what you ordered and what features, I'll initially use the LV8729. My friend has a couple of DRVs as well, so we will use those later. And then I also have a TMC3208, which can be configured as TMC2100. I'm experimenting with all these, and we'll find out how things work. So let's say LV8729, and then here the LV8729 as well. Okay, so we're done here. So what I'll do is I'll say generate. Okay, and there are no warnings in the generated output, so you can see here that it tells you what to do. So press Control A. So first you have to click inside the page, move the mouse inside the page, and then click, and then do Control A. So select it all, and then Control C, and then we will save it in a file. I'll show you how to save that Well, if you're running Windows, then you just copy that into a notepad or something and then paste it. I'll just skip that step because I don't have Windows, and it's fairly straightforward to do. Okay, so I copied the configuration file that is generated by the website into a file, and you can see that the parts there are comments, and then here are the actual configuration. It turns the STM32 on for you automatically, so you don't have it as off, and then there are the values that were generated by the generator depending on what you entered from the spreadsheet. And the rest of the stuff, there is stuff here that you can manually turn on later once you start getting to know OnStep better. Okay, so the next step would be to start the IDE and then compile the firmware using this configuration, and then loading it onto the board, and then I'll show you the board working here. Okay, so this is the CZ Mini STM32 F104 VE board, and it's a 72 megahertz board, and it has lots of pins. What we need to make it work is a dedicated chip for the EEPROM, because its internal EEPROM is first of all, it's small, 512 bytes, which may be okay for everything except the periodic error correction, but it also uses a different API because the smaller ones assume integers and things like that, 8-bit space rather than 16-bit, which can be bigger. So I have an RTC adapter module which has an EEPROM on it, and hopefully that would work. The other thing is that because this board, as you can see, has lots of pins here, lots of pins here, and lots of pins here, then it would be easy for someone to build a shield that would plug in on top of that and would have the correct routing of the pins already to the drivers, so that people can build the controller much easier than without soldering, without things like that, or with a minimal amount of soldering. You don't have to order discrete components like LEDs and diodes and capacitors and all that, and solder them and figure out the polarity and all that. So hopefully someone would take this because it's low cost. This board is about $12 or so US, and use that. So what I will show here is generating and loading the firmware on that board. So here we are. Okay, it's now focused, and what I'll do is I'll click this button which says upload the firmware to the board, and let's see the output down here. Okay, so the output is fine, and it says uploading, so you can see here that it's uploading. Okay, so it's done uploading, and even started the program on the board. If I move back to the here, you would see that as you can see here, the LED is flashing, and this LED is the built-in LED for the on this board, and you can see that it is tracking. So I'll show you one more thing, and hopefully that will wrap up the video because it's already too long. Okay, so what I have done is that I bought a cheap oscilloscope. Here it is. This is the DSO311, and it costs something like $27 US. There are cheaper versions which are around $20 US. The only difference, I think, is this knob, but they are both based on, believe it or not, STM32 ARM processors inside. and you can select a pre-assembled version or a version that you can assemble yourself. But let me show you what's happening here. So what is happening here is that you can see the light here is flashing, which means that the telescope controller is tracking sidereal rate, and we have a square wave here that says this is the output from the right ascension motor. And what I'll do here is I connected the scope to sky charts, and what I'll do is that I'll tell it to go to do a go to. So let us see if I do a go to, what will happen. Okay, as you can see, the frequency of the square wave became much higher as the scope is, the microcontroller is telling the motors, pulse, and then once it reaches the star that I told it to go to, it's doing the sidereal tracking again. So this is about all I wanted to show in this video, and I hope that someone with knowledge of hardware and maybe connections with plants that can manufacture pre-usable boards would be able to take that and productize it and make it a low cost but very capable controller that can be sold for the community of astronomers. We're used to paying high prices for things, and having open source on this and low components from China would help bring the cost down. So I hope that someone in the past, someone called Steve Sagarian on the old Yahoo mailing list for OnStep, used to make boards that would fit the Mega 2560. So if there's a Steve out there or someone who's willing to do the legwork here, I'm willing to work on getting this controller all debugged out with the RTC and the EEPROM, and then from there someone can build a shield which would make a low-cost telescope controller. Hope you have learned how to configure things using the online configuration generator and learned a few things here. Your feedback is welcome.